Hey guys, welcome back to another episode of Simuleos. Here's the thing, I apologize for starting 15 minutes late. That is my bad. First of all, I started 10 minutes late, and then I accidentally had some stuff up that I had to kind of close, so I had to restart the stream so people rewatching wouldn't see that stuff. Then, I started streaming again, but for some reason, Twitch did not accept that stream. So let me check online real quick. Good, I should be live. There shouldn't be a bit of a problem. Okay, I apologize for that, guys. Now, this is what I wanted to talk about a few seconds ago, and I apologize for being a little bit late and all that other stuff. But here's the thing. Over this upcoming week, I'm going to basically drop the number of streams that I'm doing. I used to stream every single day. Just over this upcoming week, I'm going to try something. And that something I'm going to try is streaming just Monday, Wednesday, and Friday. Now, 5 minutes ago, I did this description, but because the stream wasn't, for some reason, streaming, you guys didn't see any of that, and I apologize for that. Now, here's what I want to point out. This isn't necessarily cutting back on work for me. What I want to do instead is better prepare for every single stream, because I've been noticing lately that a lot of times as I'm implementing something, well, quite frankly, I don't know exactly what I'm doing, and I don't like implementing things when I don't know what I'm doing on stream, because that means I have to do a lot of Google searching. I have to do a lot of relying on chat to give me a solution. I do have to do a lot of things like that, and even though I love the fact that we have such a good interaction between, the streamer and the community, at the same time, I feel like it's kind of unprofessional to bring up Google so much, to go through and try to find things here and there. I mean, the truth is, the truth is, I just spend too much time thinking about things, too much time saying or whatever. I've just been thinking too much. And I need to kind of take a step back, do the thinking before stream, and then implement everything that I've been thinking about on stream. So, today is going to be the first episode that I think should be self-consistent. We're not going to rely on any other episodes today. It's just going to be FFTs today. Now, one thing I want to point out is I would like to make every single video from now on something that people can watch and learn something from. So, they walk in, and the episode title is How to Write an FFT. By the end of today, they have written an FFT. Next episode could be about how to write Noctree. So we write Noctree. And it could be that these episodes end early, or it could be that they end a few minutes late. That's okay. I just want to make it so when we go in, we implement the code that we want to implement, we get to our goal, and then we play around with the code a little bit and call it a day. That's about where we want to go, because when I've been thinking about it lately, we got the Octree stuff done in basically a day. We got the color quantization stuff done in basically a day. We got the Verlet algorithm done in basically a day. Sure, we screwed up a bit with the Runge-Kutta algorithm. Sure, we screwed up a bit with a few other things. But if we had not screwed up, we would have gotten everything basically done in a day, and we could have parsed it up into 3 one-day sessions instead of a day where we got something done, but we didn't quite finish because I didn't quite know what I was doing, and I didn't know what it was supposed to look like at the end, and then finishing it up on the next day with some sort of cliffhanger in between where we don't know exactly what's going on. So it's one of those things that I kind of want to just I want better quality streams, and that's where we're getting at here. Okay, so what is it that we're talking about today? Well, we're going to be talking about FFTs. So let me go ahead and open up Zernal, and let's talk about that. Now, if you are familiar at all with, I would say basic mathematics or engineering or physics or, well, any type of mathy thing, you have probably, and I say probably because I'm fairly certain you have, come across a Fourier transform before. Now, here's the thing. People call it Fourier transform, people call it Fourier transform. My particular accent is somewhere in between the two, and I apologize for that, but that's just how it is. So let me go ahead and open up my notes so I don't accidentally say something really stupid here, but I think that should be okay. And of course, guys, if you have any comments, questions, or concerns, let me know, and I will totally answer those as soon as I see them in chat. So first of all, what is a Fourier transform? Let's go ahead and write that one down. So Fourier transform. The idea is relatively straightforward. We take something that is in position space and we move them into something in frequency space, or some people call it momentum space, something like that. Let me see. My streams are watch me work, but I still have to prepare the work I'm going to do. Otherwise, it's just doing nothing on screen and just thinking. Yeah, I know that feeling. Okay, so what exactly does the Fourier transform look like? Well, we can display it in a number of different ways. The first way, and the way that most people are familiar with, is with some sort of integral. It looks like this. One second. Here we are. The frequency space, sometimes notated with a hat, and sometimes notated with a Z or something like that. Some Greek character, hey Marian, is going to be equal to the integral from -infinity to infinity of the position space function, again, frequency space function, position space function here, of e to the -2 I k z, x z, with a pi out front, over, oh, there is no over because it's a z, okay, there, dx, okay? So here we have a position space integral here. And we'll get into this e to the I thing in just a second. Now we also have f is going to be equal to, of x is going to be equal to the integral of -infinity to infinity of the frequency space function e to the 2 pi I x z, where we have this as a positive dz. Okay? Now z is the Greek letter. I have trouble drawing it. Forgive me. It's actually probably xi, but I can't really pronounce that one very well, so I pronounce it as z. Now, one thing to point out is these e to the I guys, right? The e to the I whatever is actually something you've probably seen before, but you've probably forgotten. And that is that these are, in some sense, a way to split our system up into sines and cosines. So let's do new page before. So we're going to say this. We say e to the plus or minus I theta is going to be equal to, yeah, there is a normalization constant that I've ignored. It's out front. It's 1 over e to the, it's 1 over square root of, well, depending on who you're talking about, 1 over square root of n or something like that. The normalization will come in just a second. But the e to the I theta is going to be equal to cosine of theta plus or minus I sine theta. So in a sense, when we see e to the I 2 pi x z, this is actually cosine of 2 pi x z plus I, one second, to the 2 pi x z. Okay? Oh, I forgot a sign. There we go. Okay. Now, one thing I want to point out here is this transition to frequency space kind of makes sense when you think about it in sines and cosines. But what we're really doing here is we're moving onto a complex plane. And one thing we have to point out about complex numbers is that they can be imaginary, right? And this is kind of hard to visualize, right? I'm going to say at this point that the visualization of complex numbers may come a little bit later, but for now we're just going to talk about the FFT, the actual transformation to and from the complex plane. In traditional physics, let's say not numerical physics, the integral works fine. But when we're moving into numerical physics, oh yeah, or 2D vectors just work fine. So we could show them as, let's see, typically what you do with imaginary numbers is this. You kind of draw a graph here, and you say we have some sort of real axis, an imaginary axis, and you kind of plot them along the real and imaginary axis. And that works perfectly fine. But again, the question of what they actually mean, I think, is a little bit too in-depth for right now, and we might talk about it a little bit different. We might talk about it a little bit differently in a little while. Okay, what was I saying before? New page before. Okay, in order to do the Fourier transform, and I'm going to notate it as FT on a computer, we need to notate it a little bit differently. And this is going to be the discrete Fourier transform. Okay, So the discrete Fourier transform is actually really interesting. So it's notated a bunch of different ways in a bunch of different texts and things like that. So I'm going to notate it in this way. We're going to say f of k, where k is our wave number that we're working with. Again, a notation coming from frequency space. Is going to equal to 1 over square root of n. 1 second. Sum of n equals 0, lowercase n, to n minus 1 of f of n, where n is our variable for position space, e to the negative I 2 pi k n over n. Okay? So the idea here is that we have a vector of n moving from, let's say, 0 to 10 in position space, and a vector of k that's moving from, let's say, 0 to 10 in momentum space. Now, the actual position of k may be a little bit different, right? So it might be that instead of going from 0 to 10, so we go from 0 to 10 in, let's say, n equals this, k could equal, instead of 0 to 10, 5 to 10, and then 0 to 5, or something like this. I just want to say that's a very interesting topic for me, who know math but have no idea how to implement it in code. Yeah, exactly the thing. One thing I want to point out is even if you've hit a Fourier transform before, it's not typical to implement one from scratch. So this is something that may be new to a whole bunch of people. So if you have questions, comments, concerns, let me know. Okay, now of course we can do the inverse Fourier transform, which I will notate like this. Lowercase f of n, again our position space variable, is going to equal 1 over square root of n. Sum of n equals 0, n minus 1. Big F of k, e to the positive I 2 pi k n. Oops, sorry about that. That's a lowercase n over n. Okay, so again, the difference here is basically the positive and negative sign in the exponential, and of course the functions being swapped over. Now, one thing I want to point out here is that this normalization is notated differently in every single book. That's kind of why I ignored it in the last one. Some people just put a 1 over n in front of the lowercase f notation. Other people don't do anything at all. Basically, the point is this normalization comes in a little bit differently for every text. Basically, I want to say, as long as you have some 1 over n in between the Fourier and inverse Fourier transform, that seems to be okay. And we'll talk about that a little bit more in a little bit. Okay, so this guy right here is the discrete Fourier transform. And basically all we did is took those integral signs, turned them into sums, and changed the variables around to be more, well, we'll say computer friendly. Okay? Now, let's talk about what we're actually doing here. So I'm going to do page, new page before, and let's write down big F of k, r square root of n. Yeah. So we're going to say f as a function of k is going to be equal to 1 over square root of n. Sum of n equals 0, n minus 1. F of n, e to the negative I 2 pi k n over n. Okay, so what is it that we're actually doing in discrete Fourier transform? This might be a little bit hard to grasp for some people, so I just want to throw this at you. Basically what we're doing here is we are creating a matrix M. Oh, that was supposed to be an M, but I wrote some sort of squiggle. We're creating a matrix M, and we're multiplying it. Oh, I see. Reciprocal score. Thanks. Sorry about that. Okay. So we're creating a function M, and we're multiplying it by our other function of real space here. So we'll say X or something like that. Now, this is actually super important that we're doing it this way. So the idea is that basically all we're doing here is creating some sort of complex matrix that we're doing the multiplication with, right? If you think about it in that way, it may be a little bit easier to grasp exactly what it is that we're doing, right? So we just kind of take our matrix, we multiply it, we sum it together. And in that case, it's kind of simple and straightforward. However, there is one big problem. The DFT is slow. To really talk about how slow it is, I think we should just implement it ourselves and then look at the difference between it and a standard Fourier transform method. So what we're going to be doing today is basically implementing the DFT, going back to talk about the FFT and how to implement that. And we're going to be doing everything in Julia. The reason I chose Julia instead of Python or C++ is simply if we chose C++, there'd be a heck of a lot of vector library stuff that we'd have to sift through. Basically, I'd have to remember all my eigenfunctions. I'd have to kind of figure out everything again. Can you explain why we take 0 and the -1 in the sum? Yes, so basically the idea is, I mean, it's kind of straightforward. Let me see. Why is the n-1 actually? Yeah, so we're going to be working with Julia. So the -1 in the sum, I'm actually not so sure about. We're hitting all n numbers here because we start from 0 and go to n-1. And so I'm assuming that this is just because we're going from a 0 base number system, right? So I tried to use it as my script language, but there's some issues for that. I find it just as good as Python for scripting. But if you have trouble using Python for scripting, like there's something very specific that you can't use scripting for. Yeah, and again, Julia is a new language, right? So there's one other thing to point out. The reason I also want to try Julia is because it's kind of experimental, and I kind of want to have fun with it, you know? So I think just because we're starting from a 0 base of Vaze, I think that's why we go from 0 to n-1. I think if this was a 1 base, it'd go from n equals 1 to n. So we could have also written it as here. 1 second. And I think that would have been the same number. Basically, we're hitting n points. And that's kind of what we're doing there. So I think it's just because we're a 0 index. Okay, so what I'm going to do real quick is get a quick sip of water. Make sure you guys don't have any further questions because we kind of went through that quite quickly. And then we're going to go ahead and implement it in code where I think things will start making a little bit more sense, right? Because quite frankly, this is not a simple thing for a lot of people. And I'd like to just kind of go through it a little bit slowly, but at the same time, I don't think it should take more than the 2 hours we typically have for stream. So I think this is a pretty good thing to do for one day. Again, gonna get a quick sip of water and let's make sure that everything is good to go. Okay, I'm not seeing any further questions, so let's go ahead and pop this over there, pop that over there, and let's cd n. Oh, good point. N, let me go over here, is the total number of elements that we have that we're working with, right? So again, as I mentioned, n is lowercase n is going to be our x space. So let's say we have a big vector from 0 to is it our period? A period. No, not quite. So it is our, and let's say we have a lowercase n equals 0, 1, 2, 3, 4, 5, 6. Capital N is going to be equal to 7, the number of elements in the array, 1, 2, 3, 4, 5, 6, 7. So it's simply the number of elements that we have in our X space grid, where our X space grid is in this case notated as n. Again, I did it this way because you'll see it a lot like this in all of your texts. In fact, my numerical physics book that I have back here notates it something like this. So it's kind of like that. More like amplitude. I guess in a way you could consider it, yeah, like an amplitude of some sort because we do a normalization in front. But it's basically, again, just the number of elements, right? So keep that in mind as we're going through. It's kind of like resolution, more like, or something like that. So that's my best way of describing it for now. You'll see it in use in just a second, and hopefully that'll make a little bit more sense. Okay, so let's go ahead and get started then. Okay, so here's what we're gonna do. I'm gonna cd into a directory, cd projects, Simuleos, and now I'm gonna make a new directory. Make directory, let's do FFT. Let's go over here, cd projects, Simuleos, and FFT. Now, here's the thing. Because I'm going to be using Julia, yeah, it is called discrete, and that is basically the reason for it. Okay, so now, when we're talking about Julia, a lot of you guys may not have seen the language before. So, what am I going to talk about first? Well, first, let's just go ahead and go into a file, and let's create, I don't know, we'll create FFT slow.jl. Oh, that was a plus. Slow.jl. Okay? and I forgot to open it up with VI. Okay, so I'm going to do what I always do. I start with the comment block, FFT slow.jl, just so I know what the comment block, or what's going on in the code, right? And I think this is a good practice for most people to do. So let's do purpose, implement, oh, one second, implement a slow version of an FFT to see how it's done. Okay, and I'm gonna very quickly put down that for this we will be using the Cooley, you're gonna love this name, guys, Tukey algorithm. Okay, and we'll get into that in just a little bit. Okay, so let's go ahead and close the comment blocks. So if I were to compare Julia to other languages, I would say it is better at number crunching than Python, but it codes like Python. So it feels like Python when you're coding it, in terms of ease to use and things like that. But its speed is actually closer to C, in that it's not like an order of magnitude off of C. It's like only 2 times as slow as C. So it's quite good for quick prototyping. Let me see. Skip slow. Oh, thanks. Implement a slow. There we go. Okay, so first thing what we're going to do is create a function, and we're going to call this function DFT slow, and it's going to read in a vector x. Okay. Now in Julia we end all the functions with simply an end command, so in that way it's kind of like MATLAB or Fortran. And what do we do next? Let me go ahead and go up here and say a super slow DFT to start. Right along column, right at the wrong column of the keyboard. Oh, is that what I did? Maybe it is what I did. But I've got a feeling, oh, it's pretty close. Okay, so what do I want to do here? Function DFT slow. Okay, so we're going to assume that x is being read already in as an array, right? So we're going to assume it's already from, let's say, 1 to 10, or some sort of list of random numbers. Now what we need to do is basically define the size of n. So we're going to say n, big N, is going to be the length of x. Okay, so now we have n, again, as I said before, as the resolution. Now we're going to say that n, lowercase n, is going to be equal to a range from 1 to n. And again, depending on who you are and how you do this, you could define this as a number of different things. For our simple case here, we're just going to define it as a range from 1 to n. And in fact, I think what we should probably do is go from 0 to n minus 1, simply because this is, I believe, more common notation. So n minus 1. Again, that was exactly the sum that we had before. Okay, so in Julia, this is going to create a, how do I put this? This is going to create a column vector, right? However, what we actually want is a row vector for this one. We are using Arch Linux for this in Victuse. Thanks for coming in. So, because we want it to be a row vector, we are now going to say n is going to be equal to n prime. Okay? And this will create the transpose of that. Now, we also want our k vector, as I said before, and this is going to be equal to n prime. So we could have set it equal to the n before, but let me just go ahead and put a quick comment in as to why we're doing it this way. Range is automatically a column vector, and we want a row vector. Okay, and one thing I'm going to do real quick is open up Julia over here and show something to you guys. So if we say n is going to be equal to, let's say, 0 to, let's say, 7, okay? We'll say that we'll now have a range from 0 to 7. If we do n prime, this of course creates the row vector like I said before, and if we do n times n prime, it creates basically the 2D array that we want for our matrix. So I'm throwing this out to you guys so that you guys see exactly what's happening in the code itself. Basically, our matrix in the end is going to be some 2D array that we multiply x by. Okay, now we have to actually create the matrix over here. So we're going to say that big matrix M is going to be equal to exp. In Julia, imaginary numbers are notated. That is because vid is 13. I am an idiot. That is supposed to be commented like that. I hadn't compiled it yet. My bad. So we're going to say exp of, what do we want here? -2 imaginary. That's how we notate imaginary numbers in Julia. Plus pi. Plus pi. Then we're going to say, actually this should be times pi, shouldn't it? -2j, let's see. It should totally be times pi. So every time you see a code in Python style, I miss semicolons and curly brackets. Yeah, all the time when I'm writing in Julia or Python, I accidentally put a semicolon or something in the back. It just happens all the time. We're using Arch Linux with the OpenBox Windows Manager DACRock 98. Okay, so now we're going to say we're multiplying this by k, this by n, and then we're dividing by capital N. Then to basically pull things off, we're going to be returning basically m times x. And that is literally the whole function for the DFT. So let me go ahead and write this. And now let me, because I'm already here, incorporate it into, it's like C answer. Okay, so here's what we're going to do. We are now going to incorporate this into our Julia prompt over here. And we do that quite simply by typing in, I believe, include. Yes, include. Include. And what do I want to do? 1 second. I over here. Include. And we're going to include FFT slow. FFT. 1 second. Slow. Oh, wait a minute. Am I in the appropriate directory? Let me go over here. For a DFT, yeah, it is pretty slow. So let me ls real quick. Oh, that's because I forgot to write it. Now let me ls. I am apparently not in the right directory. So let me write and quit. I am not. Let me cd into FFT. And now let's me move FFT slow here. Oh, here. Now I should be in the right directory. ls. And I have to just kind of tote a little bit about Julia. It's very nice in that you can do tab completion in the terminal command prompt and a few things like that. So I'm reopening up Julia. Let me close it one more time. Sorry, clear. And now let's do Julia. Okay. Now the trick here is that DFT itself is not hard, but we're going to describe why we need to do an FFT instead of just typical DFT right now. So let me go ahead and include. First of all, let's include, if I can type anything at all here, fftslow.jl. There we go. DFT slow has now been read in. It looks like MATLAB. Frank, you have nothing to apologize for, man. You are perfectly fine. Everyone here is perfectly fine. Please don't think that you're not welcome here. You just, as long as you keep everything civil and follow the rules, everything will be perfectly fine. Okay, so now we've read in the function DFT slow. And again, what's super nice about Julia is I can just type in DFT tab, bam, it's done. It's just, I love this prompt. It's very useful. So let's just go ahead and do something really quickly. Let's do X, and we're gonna set it equal to the, let's say row vector, 1, 2, 3, 4. Okay, so now we have X as an array of 0, 1, 2, 3, 4. Again, Gastron's not a bully. I think you just started off the wrong foot. Now let's do FFT of X. Okay, this is going to create this vector here, 10, 2, 2, 2, right? Okay, so what I want to do now is I want to do DFT slow, 1 second, of X. Okay, and this, let me see, matrix has 4 dimensions, B has 1, 4. 1 second. So this says we have some sort of error in DFT slow. And let me see something real quick. If I start X off as 1, 2, 3, 4, 1 second, and let me try it one more time. Yeah, okay, that's fine. So I just hadn't notated something in here. Join channel, you're not welcome here? Wait, Nixine, I said they are welcome here. My apologies if I missaid that, but I meant to say you are welcome here. My apologies. Okay, so again, this is simply because I read in a row vector instead of a column vector. This can be very easily fixed with one thing or another. Okay, so now we see basically the same thing we saw before. 10, negative 2, 2, 2, basically 0, 2, 2. And that's what we see up here. 10, negative 2, 2, 2, basically 0, 2, negative 2. Okay, so now what I want to do next. Here's what I want to do. I want to say that x is going to equal rand, and let's say 1024. There's a very particular reason I have a square root of, or a power of 2, but we'll do that a little bit later. So if we say x is equal to rand of 1024, and then we do FFT of x, one second, FFT of x, that was FTT, I want FFT, there we go, we get everything relatively quickly. In fact, if we time, let's do FFT of x, we'll see that everything happens, let's see, in about not even a second. It's all done. Now, if we do DFT slow of x, you'll see it does it quite quickly, but let me see. Let me do time here. Time. Let me see. This one took basically 1,000 times longer. So we went from 0.00011 to 0.1 second, 1374. Okay, so this is 3 orders of magnitude slower for our DFT slow algorithm. Now, I realize this is a super simple algorithm, right? How accurate is it is a DFT? The DFT is simply a discretization of an FFT. So there will be some sort of numerical error, and of course the FFT algorithm in Julia, inbuilt with FFTW or whatever it's using, is going to be better than our algorithm here. They've probably min-maxed everything, so to speak, but in general it's pretty accurate, and we'll get into the accuracy after coding up the FFT in just a second. Okay, now Happy Little Rat said a millisecond here and there. That's true, but now let's do rand of, let's do 1024 times 1024. Okay, and now we're going to do FFT of x here, and we're going to time that. FFT, one second. Okay, this one takes basically the same amount of time. If we do it with the DFT slow of x, it takes, again, about the same amount of time, but the point here is that we actually do slow things down tremendously. For my code in particular that I'm working with on, for my code in particular that I'm doing here, doing for research, I do millions of FFTs on a two-dimensional, but will become three-dimensional grid, and quite frankly, that's hard to do. That's not something that we can do like that. We've got to kind of think about things beforehand. So even though this doesn't seem like very much of a performance hit, we do need to think about speeding it up. Because again, if you're 1,000 times slower and you run this 1,000,000 times, well, this could be the difference between, I don't know, a few minutes of runtime or a few days of runtime if you're working on something very, very large. Oh, you're right, that's still 1,024 elements. Let me see something. 1,024 elements. Okay, my bad. I forgot to set x equals, my bad, 1,024 by 1,024. Let me do this again. So let me do FFT of x. There we go. FFT is no matching function. Oh my gosh, my bad. X is equal to rand. There we go. Then we do FFT of x. And this one took, let me do time. FFT of x here. This one took about 0.5 seconds, so an order of magnitude higher. And then we're going to do DFT slow of x. And this one you should be able to see, one second, out of memory error. That's something we'll have to address in a bit. Apparently, I don't have enough memory to do the matrix multiplications here. So that's another thing that you have to kind of take into account. Doing a slow thing like this probably won't work in that case. But the point is, we see things much slower. I'm really sorry, but someone linked this stream randomly, and I have no idea what it is. I'm very curious. I don't know who linked the stream, but whoever it was, thanks very much in chat. This stream is basically a stream where I do numerical physics, and that's what we do. So it is a computational physics stream. Today we're going through the FFT algorithm. What we've done so far is the DFT, and we're going from there. So, what are we going to work on from here? Now we have to talk about the actual FFT, and this is where the magic happens. So let's do page, new page before. And Linux, if you don't like it, that's fine. I totally understand it. Right now, we're going through different algorithms. That's basically the entire purpose of the channel, just to go through a whole bunch of random, how do I put this? Random algorithms and things like that that are useful to learn, and it's basically just for the joy of learning, and that's the point. I don't think you can learn math in high school. I think you can. It depends on what you define as math, right? I mean, some people define math as like algebra and stuff like that. You totally learn that in high school. But other people define math as the higher level mathematics that you need from, obviously, how do I put this? From from like college and stuff like that, which of course you aren't going to get in college, so calculus and stuff like that. If you define that as math, obviously, well, you're not going to get that in high school. Now, that said, I really do believe that you could understand it in high school. I just think that people don't give high schoolers enough credit. Oh, yeah, maybe you don't learn the math in high school. But here's the thing. A lot of people use FFTs all the time. I know I use FFTs all the time. I just never implemented one from scratch. This is the first time doing this. Okay, so how do we go from the DFT, the discrete Fourier transform, to an FFT? The most common way is to use something known as the Cooley-Tukey algorithm. Joining late, I wanted to understand FFT for a long time. Never had an opportunity to put it on the hot plate of focus. I use this in FFT all the time. Well, Sassafras, what? You are coming in at just the right time. Assuming you've seen the notation, assuming you've seen the notation of an FFT before, which I'll pop up on screen in just to show you. The FFT, let's go back here. So here's the notation of your FFT. You have something in frequency space coming from something in position space, where this is simply, you can think of it as some sort of sinusoidal thing to work. Oh, thanks, eLinux. I appreciate it. Now, I'm assuming you've probably seen this before, and I'm also assuming you've probably seen a discrete Fourier transform before. Again, we have some sort of function in frequency space, here notated with k, coming from some function in position space coming from n. James, does physics involve atoms? In many cases, yeah, especially my physics, it involves atoms. Okay, so again, guys, if you have any questions, comments, concerns, let me know, right? Because I'm going to be doing my best to describe everything as we go through it. And if you have huge questions, I would definitely like to get those questions, and how do I put this? Answer them as best I can. So can you split an atom and create radiation? I mean, splitting an atom is a very interesting way to put it. It depends on how you do the fusion or fission. It'd be fission in that case. But yeah, essentially you can do nuclear fission to create some sort of atomic bomb. That's where a hydrogen bomb comes from, I assume. I don't know. Will you have like a synopsis or links that one can stare at afterwards? I can actually provide a good link for you guys. And here, let me go ahead and give you guys that link there. So one place that I've gotten a lot of this information from is actually incredibly easy to find. If you just Google Python and then FFT, you should come up with understanding the FFT algorithm here. And this guy goes through it pretty well in Python, which I'm assuming a lot of people already know. It explains the discrete Fourier transform and then the computing of it and stuff like that. In fact, this is pretty dang close to what we're doing here. So if you have specific questions and I can't answer them here, feel free to go here because this will help out a good bit. Okay, so now, no further ado, let's get into the Cooley-Tukey algorithm. This algorithm is actually incredibly straightforward. It's just maybe not straightforward on the surface. And yeah, we're not making an atom bomb, Frank. Don't worry about it. You don't have to alert the, I don't know, NSA or whatever. The trick is solving our DFT. Again, DFT being discrete Fourier transform with recursion. Now, you might think to yourself, this doesn't seem particularly useful, but in fact, this does speed things up tremendously. So what we do first is we take our n. So let's go ahead and say we have some sort of list of n from 0, 1, 2, 3, 4, 5, 6, 7, 8, power of 2. Power of 2, I guess, would stop at 7. I'm going to start Physics University in Italy in a week, and your channel is awesome. Oh, thanks, man. I appreciate that. Good. You don't have to shut up and listen. Please feel free to ask whatever questions you have. And also, have fun with your physics in university. Have fun with your physics degree. Lots of fun. I enjoyed mine. I'm currently doing a physics PhD in Okinawa. Lots of fun. Okay, so now let's talk about what exactly we're working on here. First thing we do is we take all of the evens, which I'm going to circle in blue, 6, and all of the odds, which I'm going to circle in red, and basically split these guys up into even and odd. Okay? So even is going to be equal to, obviously, 0, 2, 4, and 6. Odd is obviously going to be equal to, 1 second, 1, 3, 5, and 7. I can count by 2s. I just can't draw 5s. Gustorn doesn't bully anyone. He's a super nice guy, Frank. Okay, so then what we do is we go through each of these, and we search through them. So let's just take the even guy as an example. Okay, we do page, new page before. And we do even, now even, is going to be equal to, like I said before, 0, 2, 4, 6, 8. Oh, there is no 8 in this case, sorry about that. And then we take the evens and odds of this one. So we take even here and odd here. So we create two new ones, which will say even and odd. So now the evens are going to be 2 and 6, and the odds are going to be 0 and 4, and we split it up again. And basically we continually split it up again and again and again until we hit some sort of resolution gap. And this resolution will be like, let's say 32, or something like that. So we keep splitting this up until we have 32 elements in our array. So we went from 1024, we split that one in half to evens and odds, so we went to 2 512s. So again, so we do 1024. We split this up into 2, even and odd. And this one splits into 512 here, 512 here. Split that up again into even and odd, even and odd. You can do the split up by filling a binary tree. Yeah, you can actually do a number of different ways to do it. In fact, what we're going to be doing is super straightforward. Julia, Python, all of the scripting languages have a way for you just to grab all of the even numbers and odd numbers relatively straightforwardly, and we'll be doing that. But in the case of, let me see, C++ or something a little bit more complicated, yeah, you can do it with some sort of binary tree, and you can search through it. You can think of it as a binary tree, and you can search through it recursively. Okay, even odd here, these split up into 256 and 256. And these again, 256, 256. And you could imagine it continually splitting up again and again and again and again until we have something, let's say down here, all the elements have like maybe 32 elements in it. You see what I'm saying? Let me know if this isn't clear. But the idea is we just continually split it up again and again and again and again and again. And then once we hit our limit, once we're at a threshold, 1 second, value, we then use another FFT. Let me see if I have this right. It's a computation for compiling or sorting data or something that has been around for years and greatly decreases the time required. Kind of, yeah. So the idea here is that we have, how do I put this? We have the FFT we want to compute, or rather, we have the Fourier transform we want to compute. We turn that into a DFT, but the DFT is slow, so we're trying to speed up the DFT, right? So we went from Fourier transform to discrete Fourier transform. We're speeding that up with the FFT, and the FFT does that with recursion. The idea is we continually split it up into even and odd, until we're at that threshold value, like I said before. We have maybe 32 elements in each array. And then when we get to that point, we implement our good old-fashioned DFT slow, which we just did a second ago, of x. And then we continually work with that. And then at the end, all we do is we concatenate everything together until we have our array back. So we basically go through. In a way, you could imagine traversing a binary tree down to its leaves at the very bottom. And then we just concatenate all of everything together. So it's going to end up being a concatenation of the following. So we'll say cat, because that's Julia notation, of a vector of x, all the evens, plus, 1 second here, our factor, which again was called m before, times all of the elements above n to 2. So this is going to be all of the, kind of like all the positive elements here, times x odd. So we're taking half of our big matrix and we're multiplying by that, and x even. Then we say plus our m big factor of n over 2, so all of the other half that we didn't use before. And again, this is kind of a mixture between different notations, times x odd. Okay, so in this way we've taken the even, 1 second, and the odd. Oh, I think I screwed that up. I think even before was blue. Let me see. We've taken the odd here and the even here. We've added them together, and then we've concatenated the entire group. And we basically keep doing that until we're through the tree. And we will show this in just a second. Okay. So one thing I also want to point out is the guide that I just linked you guys was in Python. And what we're doing right now is in Julia. So things are a little bit different, and I kind of want to show that what I'm doing here is equivalent to what the guide showed. So I may in just a second bring up, 1 second, but less ums. Yeah, I do a lot of us. Sorry about that. It's 6 in the morning my time, so every once in a while I'm doing my best not to say us and us, but it happens every now and again. So that's what we've got. We're just going to concatenate everything in the end. So what are we going to do next? Pop this over. Oh. Keep that there. And I'm also going to open up a new terminal that's going to be at the same position as this terminal over here. And what I'm going to do is bring up Python. Okay, so let me go ahead, CD projects, Simuleos, and FFT. We're doing Julia a little bit. Yeah, Gustorn. Sorry about that. I realize you like Julia a good bit. So what am I going to do here? Let me just go ahead and pull something up in Python real quick, just to show you the notation that I was talking about before. So these guys have, for a factor, some sort of range, right? In this case, it's just a one-dimensional vector, it looks like. So if I do something like this, let me very quickly create x equals 1, 2, 3, 4, 5. And I say x of, let's say, I don't know, 3. This is going to grab 1, 2, 3. If I do 3 colon, this is going to grab 4 and 5. So just throwing this out your way, that in order to do this in Python, we basically grab all the elements before 3 and equal to 3, and all of the elements after 3. So that's what I was saying before. We're taking half of our matrix, and we're taking the other half of the matrix. Now, in Julia, this is done a little bit differently. So let me say, I'm going to define x. Again, I'm trying not to say us, guys. I apologize for that. And we're going to set it equal to the row vector here, 1, 2, 3, 4, 5, like we said before. Now, if we do x of, let's say, 1, I think 2 to 5, this should do it, but let me check something real quick. 2 to 5. Again, my Julia is a little bit rusty here. This will give me 1 and 4. That's because it's a 3. I wanted to do 1, 2, 5. So this gives me all the odd numbers. And of course, if I start at 2, it'll give me all the even numbers. Okay, by the way, what is up with Programming Language Designer? It's like they can't come up with a good searchable name. I mean, I don't know. I can't help you with that one. But that's how it goes. Okay, so that would get the even and odd. Now, Frank34, feel free to ask whatever question you have. Now, if I want to grab all of the elements from, let's say, 2 to 5, I can just do it this way. So we'll grab all the elements from 2 to 5. So to grab all of the latter elements in the array, the best way I found to do it, although maybe you guys have a better way to do it, maybe you guys are Julia whizzes, is simply to say, okay, we have 5 elements in the array, and we just grab 5 over 2, and we either floor or ceiling this. So we'll say floor here. And I realize it's kind of messy. Let me see, indexing non-integer reals. Oh, my bad. Let's just say 3 to 5 or something like that. 3 to 5. And this will grab 3, 4, and 5. And then we can do over here 1 and 2. So this is what we're going to be doing. We're going to be grabbing, what am I going to say here? We're going to be grabbing half the array and the other half of the array for the concatenation. Just add language, and you'll usually hit programming language, sometimes fail horribly. Something like make the computer do something in a gobbledygook language with obscure syntax. Okay, so now let's go through and let's do our algorithm. And we should, again, be able to get this done by 7. I see no reason why it should take longer than that. And then we can just play around a little bit with it. One thing I'm going to do real quick is open up PyPlot. 1 second, just so we have it up. Okay, now let's go ahead and implement the Cooley-Tukey algorithm. 1 second, Cooley-Tukey. 1 second, Tukey algorithm. And I don't know exactly the best way to notate this. An honest programming language names? How to stop worrying and learn to love single letter variables? Gosh, I hate single letter variables though. I really do. Like this actually kind of is a, if it's mathematical notation, it's fine. I understand, but I don't know. So I'm going to notate this as Cooley-Tukey. That's what I'm going to call it. So function Cooley-Tukey. And actually, guys, very quickly, let me make sure I'm not misspelling Tukey's name. So let me go over here, Tukey. Okay, good. It is Tukey like that. Okay, Cooley-Tukey. And what do we need to read in? Well, we need to read in X like we did before. And then we end it over here. Now again, guys, this is the first time I've ever implemented the Cooley-Tukey algorithm. So forgive me if I mess something up. Okay, so first thing we need to do is we need to say n, big capital N, is going to be equal to length of x. Pretty straightforward. Is the most used bashing in the world, but it's still kept relatively quiet. Bashing is in the language. Sorry, I don't know if I fully followed that comment. My apologies. Okay, so what I want to say is this. I want to say if how do we do the modulus in Julia? I think it's just 2 mod 4, 3 or something like that. Yep, okay. Let's say 2 mod 5, 2 mod, let's say 10 mod 2. Okay, good. That's what I want to see. So what I want to say, just at an FFT, yes, totally fast Fourier transform. We're doing that. It does actually, right? The Cooley-Tukey algorithm is like the coolest Tukey name. I don't know where I was going with that. I apologize. But it is one of the coolest names for an algorithm I've seen. It's just super fun. But basically the idea here is we're solving DFT with recursion. Grenatapple, if you're wondering. And we're just now doing the implementation of the algorithm. So again, you're coming at a good time. So what we're going to say is if n mod 2 is not equal to 0, then, and over here, we are going to say, it seems like, well, that's good. What I'm going to say is I'm going to print line, and there are probably more efficient ways to do this. Again, just my Julia is a little bit rusty. We're going to print line must be a power of 2. Exclamation mark for emphasis, and then we're just going to exit 0. So let's go ahead and read this function in, write this, go here, and let's do include, what do I want? It's FFT slow. And let me see, end in function, if, oh shoot, did I forget how to do if statements in Julia? If expected end, a definition of Cooley. Let me see. Definition function of Cooley, function Cooley. I don't have a function Cooley. Well, loading simulate as FFT slow and expression starting on line 9. We go to line 9, function Cooley-Tukey. Maybe I should do an underscore instead of a dash. That might have been the issue. try that. Okay, good. So now if I run Cooley, 1 second, Cooley-Tukey of, and let's say 1, 2, 2, which is not a power of 2, it doesn't do what I expected it to do. Oh, but that's because x needs to be that. So let's say x is going to be equal to, let's say 5 elements, 1, 2, 3, 4, 5, 6. Let me see, length of x is 6. So now if we read in Cooley, 1 second, Cooley-Tukey of x, we will see must be a power of 2 and Julia exits. Just popping that up there. If you don't have power 2 data, do you pad it with zeros? Yeah, so that's typically what happens with an FFT. You will pad the excess with zeros, but in our case, I didn't want to necessarily do that just because it's kind of an example. So let's do Julia again. Maybe I shouldn't have exited 0, but that's okay. So let's go down here. Let me check something real quick. I kind of forgot how to do if statements in Julia, so let me say if x equals 5, if, let's say, x equals 5, I don't know, print a, else, print, 1 second, yo, just 1 second, I totally forgot, and now we pop this up again, we see x equals 4. Yeah, so that should be good. Now the else if is the question I had. So let's say else if. Okay, if else. There we go. Good. Fantastic. If you don't have power 2 data, yeah, you can't subtract Tukey from Cooley. Yeah, that's totally the problem we had before. Okay, so this will just exit the program if anything happens, if we're not a power of 2. Now, let's do this. We say else if here. If else. I just totally forgot which was if else. Sorry about that, guys. And then else. Okay, so if else, and then we have to end everything down here. So we're going to say end. 1 second. If, let's see, x less than y, print line, x is less than y, else if y. Let's see. Print line, x equals y, and don't need the parentheses. Probably not. But I don't know. The parentheses make it a little bit clearer to me. I think. Maybe it doesn't, but it's a little bit clearer to me anyway. Okay, so now we're going to say if else. And what do we want here? N is less than the resolution that we're reading in. And I'm going to just arbitrarily define the resolution as 32. Okay? It is arbitrarily defined here. What we're going to do is we're going to return DFT slow of x. Okay, so this is again the idea that we're beneath that resolution. Now we do the magic part of it, which is in this else statement here. And this is, again, maybe a little bit weird to some people, maybe not. So here's what we're going to do. We're going to grab all the x evens, and we're going to set this equal to the FFT of x. And we pull all the evens. So we start at 2. I know, Gustorn, I did the same thing. Last night, actually, the reason I was up late this morning, again, it was like 5:15, 15 minutes late when I started the stream, was because last night I was like, oh, this is super easy to implement in Julia. And then I implemented it in Julia, and I was like, crap, I totally forgot about Julia's syntax. Completely forgot about it. So we want to grab all the evens. One thing about Julia, it starts counting at 1, not 0, 1. So the first even is going to be 2. And then we're going to go to n, something like this. Then we're going to grab all the x odd, and we're going to say this is going to equal to FFT. Oh, why am I doing FFT? This should be, my bad, Cooley-Tukey. My bad, it's notated differently in my notes. Cooley-Tukey here, Cooley-Tukey there, of x. And then we start counting at 1, 2, 2, n. There we are. I mean, it's easy to implement. Return FFT x. Yeah. So what do I want to do next? Now what we do is we create our arbitrary factor that we're working with. And even though I notated it in my notes as m, it's not quite m. And you'll see the difference in just a second. So I'm going to call it, instead of m, I'm going to call it factor. And I'm going to say it's going to be equal to exp of -2 imaginary. 1 second. We got scripts in Fortran for this and use them for calculations of seismic functions. Fortran looks somehow different than this. I'm confused. Wisdom left me. I'll be honest. Fortran is... I don't know. I like Fortran. It's one of those languages that I can't bring myself to dislike. A lot of people hate it. I just can't bring myself to hate it. It's such a fun language to code in. In fact, my roommate is now coding in Fortran, and he's always hit and miss. One day he's like, oh, I like this, and the other day he's like, I hate this. It's the best thing in the world. Okay, so what do I want to do next? We're going to multiply this by pi. Multiply it by the basically range from 0 to n. So let me go ahead and create that real quick. We're going to say, just like we did before, n is going to be equal to the range from 0 to n. So it's going to be 0 to n minus 1, like we did in the sum. And we're going to say, because it needs to be a column vector, n is going to be equal to n prime. Actually, should it be column or should it be row? We'll see. We'll see. Worst comes to worst, this doesn't work, and then we do something else. Okay. Fortran is the best language designed for its purpose. Yeah, sure. So that's the thing, right? Fortran is made for physicists, and it works well with physicists. Okay, then we divide this by n in the end. The difference here is that we don't have a k anymore, so that's the big difference between the factors here. And then finally, in the end, we return the concatenation we said before. So this is going to be cat, and in Julia the notation is 1, and then we give what we're concatenating. For example, we'll say x here, and we'll say, how about x is going to be equal to 1, 2, 3, 4, 5. And if we want to concatenate x, we'll say cat of 1, x, x. And this will give us 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Hey, Ztoko, thanks for coming in. Let me see. Of course, it's old and has problems because of that. Fun till you reach the 70-second character limitation and forgot about it in one. Yeah, no, I know that feeling too. Yeah, we're doing FFTs. So we're going to do concatenation of the following. So let's go ahead and do it. It will be these two guys. So we want x even plus the factor times times the factor, the second half of the factor. So because this factor is kind of large, we're going to say the following. So we're going to say up here, we're going to define the variable. Actually, yeah, let's define it in here. Let's say half is going to be equal to floor of n divided by 2, just so we have it there. And we're going to say half to n. Okay? And then the other one's going to be basically 1 to half. So we say 1 to half, and we multiply this by x odd. X odd. And again, we might have something weird about the column and row vectors here that we need to take into account. While using Julia, not Python or C++, just a personal preference. Honestly, yeah, at this point it is just a personal preference because we could use Python equally as well for this. In fact, we could use C++ too. The reason I wanted to stray away from C++ for this one in particular, again, we typically do C++ on the stream, but simply because matrix multiplication of complex numbers is not the most trivial thing to do in C++. It's not that it's not trivial, but it takes some getting used to, and I figured this notation is a little bit easier to read. The idea here is to understand the FFT, not to understand the language underneath it. Totally not Zuki, thanks for coming in. Trying to remember if Cooley-Tukey was one with the -1, 1, -1, 1 matrix thing. I'm not sure. I'm not sure. Yeah, that's exactly right, Happy Little Rat. So we could use eigen or something like that. Okay, x odd, and then we concatenate it with x even. And just to show you guys a difference in notation, here, I think I can do this. Maybe I can't. First of all, I need to lowercase this, so our x. Now we're going to say x even. Oopsie, my bad. We're going to say x even plus factor of the other half. So we're going to say 1 to half times x odd. And that should be the concatenation of it. Now, just to show you guys in Python how this is done, because some of you guys may have questions, let's go ahead and say x is equal to that. In this case, we have to pull in numpy. So we're going to say import numpy. Okay, and then we're going to say numpy. Oh, let me do import numpy as np because that's typical. Then we'll say np, 1 second, dot concatenate I think that's how you spell it. And then we give it what we want it to concatenate. So we'll say x and x. And this should be right. Yeah, so that concatenates the two. I'm contemplating whether to add prime syntax to my script. Probably not. It's up to you guys. I mean, it's something that's super useful if you do a lot of math, but if you don't do that much math, it's not so big of a deal. So this should be the Cooley-Tukey algorithm, but we may have a bit of a problem because I may have mixed up rows and column vectors and things like that. So let me very quickly write that and then do the last include, which will be including, let me see, FFT slow, deprecated if else. Use if else parentheses. Okay. 1 second. dd x include. There we go. So now we try Cooley-Tukey. And first of all, this one should break because x is not a power of 2. Good. So now let's open up Julia. And let's import it one more time. So let's grab the last include event. Now we're going to do x is going to be equal to, let's do 0, 1, 2, 3. Okay, it's a 4-element array. And let's do Cooley-Tukey of x. It must be a power of 2. Now that's interesting because it totally is a power of 2. That's rather interesting. 4-element array. So let's go in here and let's print some things while we're working with this. So let's do the following. Let's do print line n. And let's go over here, Julia, include x is equal to 1, 2, 3, 4. And let's do Cooley-Tukey. It says 4 and it says it must be a power of 2. So let me try something real quick. Let me go over here to Julia. Let me do 4. Oh, 1 second. This should be not equals to 0. That would totally explain the issue. My bad, guys. Let me go over here. X is equal to this. Now we do Cooley-Tukey of x. Error defined value Cooley-Tukey not defined. Okay, good. So let me see here. Funny thing is that it's a mix of Python and Julia syntax. I think you just omit the parentheses in the loop and the headers. And now here you're talking about both for basically the reasons I picked up, i.e. graphics program using a lot of simple vector math. Okay, so let's see what we got here. So the issue is that for some reason Cooley-Tukey is not defined, which is kind of weird to me because Cooley-Tukey should be defined. Oh, it's probably because I forgot to include it. That's the issue. My bad. Now we do Cooley-Tukey of x, and good. So we did 4, 2, 1. Okay. So what we should have done here is something a little bit different. Let me see. So if else n should be here, we should be going into this loop here. So let's do print line DFT slow. Just to check something up. Okay, let's write this, go over here. Julia again, include what we were including. Run the last x. And now we're going to say, what do we want? Include Cooley-Tukey of x. Yeah, so for some reason we're not getting in here. N is totally less than or equal to 32. But I think it's because we're in an if-else statement instead of this. So let's go here. Let's just put an end here. And let's just change this to if and else. Now let's go here, Julia. Okay, this one should work. No problems. Let's do include. And then we're going to do Cooley-Tukey of x. Error defined, undefined. I didn't define x. 1 second. Now we do Cooley-Tukey of x. And we return exactly what you would expect. Now, let me see. Interesting, I've never seen Julia. Got some D&D. All right, eLenix, I will see you around. Thanks so much for coming in. Good, so now we have the DFT slow working. Let's see if we can get the actual Cooley-Tukey stuff done. Now, let me check just to make sure that this is correct. Let me do FFT of x. And we should see 6, 0, negative 2, 2, 2, 0, 2, negative 2, negative 2. Exactly what we'd expect from the FFT. Now, what are we going to do next? Let's make this x a little bit larger. So let's make it 64 in length. So we're going to say x is going to be equal to random of 64. There we go. So now we have our random 64 array. And let's just do a very basic one here. So we're going to do Cooley-Tukey of x. And let's see. So now we have a bunch of issues. It's a pretty common trait amongst interpreted JIT languages. Can test without compiling. Yeah, so this is a just-in-time compiler like Python. Okay, so indexing with non-integer reals is deprecated. It may be that your index arose from an integer division, form I. Let me see, what is the issue here? So let's see where we have this issue. It could be in this guy here. So let me do a quick print line. Checking. Let's go over here. Cooley-Tukey of, we have to include it again. 1 second, include. Now we do Cooley-Tukey of X. And checking. Okay, so the issue is in this half here. Let me see. So I'm learning a bit of that stuff now from you. Yeah, Gustor knows just about everything we need to know here. So, floor of n over 2. So the issue here is that, for some reason, that is not an integer. So Cooley-Tukey at FFT slow 29. Yeah, so the issue is in this half value there. Okay, so this is an issue with Julia syntax. Give me just a second to fix this up. And let's see what we have here. So we're going to say x of is going to be equal to, let's say, 1, 2, 3, 4, 5. And I want to say 5 divided by 2 is 2.5. Let's do floor of 5 divided by 2. Oh, 2.0. So let me do, how about, instead of 5 divided by 2, let's do int here. So int of floor. There's probably a better way to do this, but, oh, 1 second. Int of floor. I'm so used to Vim that I'm having trouble with this. And let's see. Nope. Here. Premature end of input. So let me do int of floor of 5 divided by 2. There. 2. That's what I want. Now let me do x from int of floor of 5 divided by 2 to, let's say, 3. And this should do it. There we go. 2, 3. Good. So it was just an issue with the integer values. So let's do int of floor. I could probably also do 5 divided by 2. Yeah, that probably would have worked. Let me see. Int of 5 divided by 2. No. Okay, good. Let's go here, write this, and let's try including it one more time. Where's include? Let's try Cooley-Tukey of X. Must be a power of 2. Oh, of course. Let me go over here. Control D. Julia. Okay, sorry about that. Let me see. If you guys, of course, have any questions, I apologize for kind of messing around with Julia a little bit here. I should have had this done beforehand, but I failed to prepare that this morning. Anyway, so let's go to include. Here, include FFT slow. Now I want to say x is going to be equal to rand of 64, so we have 64 random elements. And then we're going to say Cooley-Tukey of x. And let's see, what do we have here? We're calling 2 DFT slows, and it looks like we have a bit of an issue. Int x is deprecated. Use rand int x. Instead, round int x. Okay, so you want me to use round? That's also okay. Let's go to the last include. And let's Cooley-Tukey of x. Indexing with non-integer reals is deprecated. Dagnabbit. Anaconda is something like IDL. I've used IDL before, but yeah, it's not something I've used in a while. So let me see. It says the problem is in a 28. Here, so it says return concatenation of half n. Okay, indexing with non-integer reals is deprecated, but it should be an integer real. Oh, that's because I changed this to an int. Okay, so let me see what happens if I change this back to an int. This is actually kind of weird. Let me go include FFT slow. Let me Cooley-Tukey of x. And let's see, the issue is now in 28 again. It says abstract float is deprecated. Use round of int x. So we want to do round of int x. Include again. Cooley-Tukey. Error star has no method matching array float and array complex. Okay, so I think the issue here is this. Let me change this to a dot multiplication. Kind of like MATLAB syntax. Write this, go over here to include. Cooley-Tukey. Okay, and finally dimensions mismatch. Let me see. Just divide n2. Will that do it? Let me see. Divide 5 divided by 2. Let me do 2. 2. Oh, if that does it, that does it. Let's do that. I have to go to bed. I'll see you around, Hafaze. Thanks for coming in. So we'll do divide n and 2. And 2. Okay. Let me see. Tebroa, at least on Fedora. If you're on sudo anaconda, you're going to have a bad time. I think, I don't know. I know anaconda is not so bad. So let's go here, write this. Dimension mismatch arrays could not be broadcast to a common size. Let's see here if we do include Cooley-Tukey of x. Yes, so we're having the same issue. Let me try defining n a little differently. Let's go to Cooley-Tukey, include Cooley-Tukey of x. Let me see, dimension mismatch array could not be broadcast to a common size. So the issue here, let me think, it should be that factor is half. So let me go through and let me do a little bit of debugging here. Again, guys, I was not anticipating having the debugging. I should have prepared this last night, but I didn't. Oh well, that's okay. Lesson learned. We will do this again next time. So what am I going to say? I'll do a little bit more preparing next time. So what do we say? Return concatenation of 1 factor half. So what I want to do is I want to do this. So let's say it could be that it's inclusive. So what do I want? Let me do x is going to be equal to 0. Oh, let's call it something else. We'll call it y is going to be equal to, what do I want here? Let's do 0, 1, 2, 3, 4, and there we go. So we have 5 elements in y. Now we're going to say, let's see, how about, what do I want here? We're going to say z is going to be equal to, let's say 10 elements. So we're going to say 0 to 10 minus 1. That's going to be 10 element array. Now, what do we want to do here? We're going to say, let's grab half of 10. So we're going to say half of 10 is 5. And I want to say factor. So we're going to say z of 5 to 10. How many elements is that? So let's say length of this. There we go. So that's 6 elements. But what I actually want is 5 elements here. So let's do this. Let's do half plus 1. And then we're going to do 1 to 5. There we go. That should work. Now let's go over here and let me see. How many elements are in x odd and x even? It should be the same number. So let's now do x is going to be equal to rand of 64. Here we are. And now let's do, 1 second, Cooley-Tukey of x could not be broadcast to a common size. Great. Okay. So we have y and z that we're working with here. So let me do y times z. See what we get there. Absolutely nothing. Y dot times z could not be broadcast to the same size. That's the issue that we're currently having. So let me do y times z of, and let's do 6 to 10. Okay, that one does work because they are the appropriate size. So this means that I have a bit of an issue with the size that we're going with here. So let's see, what do we have? X odd. I guess we can just print out the sizes real quick. So let's go here and let's do print line length of, and let's do X odd. And we're going to do the same here, length print line of length. And what it says, it's on 41. Oh, it's actually down there, really? 1 second, let me change something up real quick. 41? It says it's down here. Let me try this again. Let's go here, 1 second. Include. Here we are, Cooley-Tukey. There. So the goal of the day to explore FFT algorithms, mathematics, or some sort of optimization. It's basically just to implement an FFT from scratch. That's kind of the idea. I've never done it from scratch before. Okay. And let me see here. Cooley-Tukey of X actually seemed to work that time. Huh. Okay, well, apparently, whatever the error was, it was because I forgot to include it that time. So let me include it one more time. Just to be sure, the Cooley-Tukey algorithm does seem to be working right now. Good. Okay, so we took a 64 element array, and we went from there. Now, I apologize for kind of, you know, messing up here and there, but that's okay. That's kind of the nature of streaming and doing it live, especially when, again, I've never done it before. I just had notes to work off of. And the notes, again, were in Python, not Julia, so there were some issues there. Now, we should have this actually working, so what I want to do now is I want to do Cooley-Tukey of X minus FFT of X, and we should see that these guys are pretty close to 0, but they are not actually. And that's important to note. So FFT of X is going to be equal to this here. And let's see. Let me do something else then. Let me do, how about X is going to be equal to something very simple here. So we're going to say 0, 1, 2, 3. Okay. Now we do DFT slow of X here. And we do FFT of X there. Okay. That is correct. So the DFT slow is correct. Now, if we do anything bigger than our than 32, we run into some issues, I bet. So let me drop this down to 2. And let me go ahead and write this. And now let me do the Cooley-Tukey algorithm of X. So we're going to do Cooley-Tukey of X. And this is going to be us kind of debugging a little bit. Actually, for the Cooley-Tukey of X, we are good. We do the 4-element array. That should be fine. Okay, so now let's see, what do I want to do next? Let's change X, and we're going to set it equal to the range from 0 to, let's say, 8 minus 1, so 7. Okay, now we're going to do Cooley-Tukey of X, and now we have a bit of an issue. And I think it's because what we need to do is X. Let me see. X is going to be equal to X prime. X equals X prime. Now let's try Cooley-Tukey of X. Okay, so the issue here is that you haven't re-included with after the change. After the if change? Maybe not. Let's go here, right here. Yeah, fair enough. You're right, I didn't. That would be the issue. Include here. Now let's try Cooley-Tukey of X. And let's see, what do we have here? So these guys are clearly different. So this is an issue we need to fix. I remember in the 90s it was cool when someone uncoded an image or audio track. That's basically how I learned about the FFT. Yeah, that's fair enough. Good, thanks Gustron for catching that. You're right, we did not do the algorithm correctly. So now let's go back to our previous definition of X from 0, 1, 2, 3. Let's do Cooley-Tukey of X, and we have the following. We did 2 DFT slows, and actually that one doesn't look so bad. So let me do an FFT of X. Oh, actually that's clearly wrong. The first element is not correct. 2 minus 2 times e to the negative 16th, 2 minus 2, yeah, so that's not right. Oh, actually, wait, it's just mixed up. We have 6.0, negative 2, 2. Okay, this is literally just mixed up. How about we do this then? When we do the concatenation, we do 1 to half, and then, sorry about that, 1 to half, and then half plus 1 to n. Now let's try this, include that. And let's do, I suppose that's obvious, isn't it? Now we have exactly what we expect. Let me do FFT of X for a very small scale case. And it should be 6, negative 2, 2. Oh, shoot. Is that a negative 2? Minus 0. Negative 2, 2. Okay, so let me try this one more time. 1 second, x plus, yep, that looks right to me. X odd, again, that looks right to me. Let me try one thing real quick. Let me do DFT slow of X. That is definitely a negative 2, and that is definitely different than what I'm getting with the Cooley-Tukey algorithm. Yes, okay. So, let me see. So now we have an issue with that. And let me see what we can do there. So the issue has to be in that concatenation, I think. X even factor half. So let's just go ahead and print something out real quick. Let's print, we have the concatenation there. Let me just print a couple things here. So let me do print line. And I want to print line factor. And actually, maybe that's the issue here. 1 second. Well, you should really add some spaces around those math operators. Yes, I will in just a second. Let me check something real quick. Okay. And here. Let's go here and let's do the last include. And we'll do Cooley-Tukey of X. Okay, so that didn't help anything. I thought maybe it would. So let's see. Delete this line. Let's try it again. Include Cooley-Tukey of X. No. Okay, for some reason I thought that would help, but it doesn't seem to be helping at all. So we have -2 imaginary times pi times the range, so that's going to be n over n, x even plus factor from 1 to a half. Good. X odd. Good. X even times factor. So let me print out a couple of things like I was saying before, and we'll see if we can get this right. So we're going to do print line factor, and we're going to print line of, what do I want here? Print line of, I guess x even and x odd should be, should be straightforward here. So let's just print line of the factor. And let's go ahead and include, and then Cooley-Tukey of X. Okay, so it's complex. And maybe this is, let's just do print factor. Include Cooley-Tukey of X. Oh, that didn't help at all, did it? Line here. And let me do factor and print line of X. No, X even, X odd. Let's do X even. Now let's do include Cooley-Tukey of X. Okay. Complex. 1, 2. Good, it has 2 elements in it. What do we have here? It looks like it has 1, 2, 3, 4 elements in it. Okay, so it seems to me like the factor has 2 extra elements in it than what it should have. So, why would that be the case? You're never defining n prime? I don't know what you mean by never defining n prime. Sorry about that. Go over here. Include Cooley-Tukey of X. Okay, well guys, this was me not preparing well enough. I should have done this beforehand. My apologies, guys. We'll see how this goes in just a second. Let me get some water. I'm kind of losing my voice, and then we'll go from there. Okay. So, never defining n prime. Again, I don't know what you mean by that. So let's say n is going to be equal to, let's just do this real quick. So we'll just kind of do the algorithm and see where it breaks. I don't understand what you mean. N prime shouldn't have a value? N prime does have a value. Like x prime has a value. I'm confused as to... Again, I'm super confused as to what you mean. I defined n, and then I gave it... n prime does the transpose of the vector that we're working on, right? So we have x, and then it turns into x prime. Right, so x prime does the... it's defined in Julia. So that's... I guess I'm just not following what you mean. Okay. So we currently have this issue here. Okay. Yeah. So let's go ahead and close this. And actually, guys, we probably don't want it as the transpose. I'm trying to think here of what we actually want here. So we have a column vector that we're reading in. No, it's no problem. Absolutely no problem, Gustorn. Okay, so what do we have here? We're reading in a column vector of x, right? It is a column vector to start. N is equal to the length of x, which is going to be equal to 4. We print line n, which is 4. Should be okay. Now we say print line must be a power of 2 if it is not a power of 2. It is in most cases. If we have less than 2, though, that means we've split further. we're going to be doing DFT slow. So if we're equal to 2, if we're on 2. Now we say x even is going to be Cooley-Tukey of 2 to 2 to n. Okay. And this should be fine, right? So we should be pulling x even and x odd. No problem there. Now, what's next? N is that. So the issue here that I'm seeing is that x even seems to be smaller than the factor. So let me just do length of factor here and length of x even here. And let's do include. And now Cooley-Tukey. Okay, so it looks like I'm printing out too many numbers. I don't know what's actually happening here. So let me see. Let me go to n length of x. Where's the print line? Must be a power of 2. Print line n. Oops. Go over here. Include. Cooley-Tukey. Yes, so that is the issue. For some reason, n, let me see. Lowercase n is of length 4. Oh wait, maybe it should be of length 4. Let me think. 2n over n. Let me see. How do we define n? We define n as a range from 0 to n. Shoot, never mind, that's okay. This is me being an idiot and not remembering what it is that we're actually doing here. So let me see what happens if we go down here. And let's see if we just change these to multiplications instead of dot multiplications. Julia, sorry about that. Do the last include event. No, okay. I thought maybe we could do that. I wasn't sure. So now we're going to do Cooley-Tukey of x. X is not defined. Oh, x is going to be equal to 0, 1, 2, 3. Now we're going to do Cooley-Tukey of x. Yes, so I thought that would be an issue. Okay, so again, I'm not exactly sure what the issue is here. It's going to be me fiddling around with the code. I apologize for that. So what I'm going to do instead is this. I'm going to very briefly talk about what the FFT is actually doing here and why it's important. And we can come back to this in a bit. I mean, the crux of it is here. I don't know. I messed up on the end. But that's okay. So let me very quickly do this. So let me say this. I'm going to be using pyplot for just a second. Using pyplot here. And this will allow me to basically use some graphing software from Python. Now, just so you see how the software works, let me just do plot of x. And you'll see it will bring up a graph of plotting x. So what I want to do now is I want to basically populate x with a value. So we're going to say x is going to be equal to 1 second. 1 second. Here we are here. X is going to be equal to the following. Sine. 1 second. Sine of 2 times pi times I divided by S is what I wrote here, but I want to do 128 for 1 second. I equals 1 to 128. Okay, and that there. And this will create basically a sine wave. If we plot x, you will see a sine wave here. Now, if we do plot the FFT of x, this is where things get a little bit interesting. So if you plot the FFT of x, we get one peak right over here and another peak over here. This is again because of the way we've discretized our k-space, as I mentioned before. Now, what we can do here is if we change the frequency here from 128 to, let's say, 64, and then we plot that, you see that the peak kind of changes a little bit. So what I want to do is keep this up over here and change our x value. So let's go from 64, let's go back to 128 here, and now let's plot the FFT of x. You'll see that we went from this green to that blue, but that's kind of hard to see. So let me go to, let's say, 16. And now let's do plot FFT of x. And here you can clearly see we've changed. Our values are coming in further and further. But now I want to do something a little bit different. I want to do plot the absolute value of the FFT of x squared. I think it's dot slash dot squared. here. And basically what I want to point out here is that this is a way for us to go from real space, where we have some sort of sine wave and some sort of frequency, some sort of oscillation, and it's a way for us to find those oscillations. So this gives us the frequency of the oscillation we're working with. So we went from 128, we divided that by, let's say we divided that by 16, right? And so the frequency is going to be 128 divided by 16, which is 8. And so this is at the value of 8. As you can see down here, maybe you can't, but it is at the value of 8. So if we redefine x one more time, and we define it as maybe divided by 8 here, we would expect the frequency to be twice what it is before, so 16. Let's go ahead and enter here. Now we're going to plot absolute value there. And here we see it's pretty dang close to 20 down here, so it's closer to 16. And of course, we can do it even further. Let me go ahead and accidentally plot it again. Let's do this, and let's change this to, I don't know, 2. And now we're expecting to be at position 64. So if we plot this one, we well, we don't see anything, but that's an issue with the resolution. So let's go to 4. Now let's do plot absolute value here, and then we see 32. And this is kind of the point that I wanted to throw out. The interesting thing about the FFT algorithm is it allows us to go from real space to phase space. It allows us to find the phase of our system. And this is how it's kind of seen, right? We see these delta peaks in the in momentum space. And that's kind of neat. This is what STAM did with computation fluids to optimize simulation when went and patented it, and now nobody uses that method. Actually, there are some very interesting methods with fluids that use complex analysis, mainly conformal mapping, which is something I wanted to get into later, which is why I kind of wanted to do a stream on FFTs. Now, let me see if I can figure out how to finish up this FFT guy, and then we'll go from there. So let me go ahead and figure out what goes from there. If you have further questions, let me know. We can continually plot that, but basically the idea was that we can, if we know the frequency of the sine wave in Fourier space or in phase space, it would be a delta peak in phase space. So basically we've taken our system. So if we have a whole bunch of different, let's say, oscillations going on with our sine wave, so it changes or something like that, we can actually pinpoint exactly what frequencies are happening. So if we have a whole bunch of sine waves added together, we can tell those frequencies. So here, let's just do that. Let's say x is equal to this, and then x plus equals something else. So that was what we just had. So let's do plus equals sine, and we'll add, I don't know, let's do 8. There we go. And now let's do plot FFT absolute value there. And you see we have 2 peaks. And these 2 peaks correspond to both of the 2 frequencies that we just added in together. So we added in one that had a frequency of about 16, another that had a frequency of about 32. And you see we have 2 peaks of 16 and 32. So we have a sine wave that is a combination of these 2 frequencies. In fact, let's go ahead and close this plot. And let's just plot x. And you'll see that x looks kind of funny, right? It's a mixture of these 2 different frequencies. But it's actually relatively straightforward, right? Because all we have to do is plot this, and now we have those 2 frequencies. So we just went from real space to Fourier space. Let's see what happens if I plot x here. Okay. Good. So that's kind of the idea. Do you know about Vim? I use Vim all the time. My math is like I've heard of a sine before. Oh, so here, let me just redo that then. Let me see. Let's add another oscillation on here, which is just going to be divided by 128 here. And now let's plot x. And you see we have a big oscillation here with 2 smaller oscillations here. And we can pinpoint each of these frequencies with the FFT. So we do plot absolute value squared of that. We see 1 peak here, 1 peak there, 1 peak there, and that's our 3 frequencies. And so that's the power of the FFT. That's why we want to do it. It's the power of the Fourier transform, actually. But with the FFT, we can do this incredibly quickly. And that's kind of the idea. Now, I obviously have a bug in my implementation. I can fix this up and show you guys next time. But I think this is just going to be me messing around with Julia a little bit. But the heart of it is here. We have all the elements here. There's just something wrong with the way that I'm currently implementing it. So there's something wrong with the syntax there, and I'm not sure exactly where that's coming in. So I need to kind of take a look at this off on the side. But again, this is why the FFT is so powerful. It allows you to do that kind of stuff. So guys, I want to take just 1 minute, no longer than a minute, talking about what I want to do this upcoming week. And that is, I actually want to make sure I have adequately prepared for each of my streams. This one I clearly did not prepare for. Not enough anyway. I would like it so that I have almost completely coded up anything that could be an issue before doing the stream. Although I want it to be that the stream itself is the first time I've implemented it fully, so that I'm still experiencing with you guys, but I've done basically everything but. You think it's a problem with the XOD slicing? Let me see. XOD? It could be, so let's see what happens. So I'm gonna do X. So I'm gonna do X is gonna be equal to, let's do 0, 1, 2, 3, 4, 5. Here we are. And now we're gonna say X of 1 to 2 to 6 here. And we get 0 to 4. Oh, first element. Yeah. Most agree with the above statement. Now we want to do 2 to 2 to 6. 1, 3, 5. Which is right. When did I start using Vim? Vim is the only text editor I have ever used, actually. So let me count this 1, 2, 3, 4, 5, 6, so it's a little bit more obvious what's happening here. Okay, so if we grab all the evens, it is of course all the evens, and if we grab all the odds, we grab all the odds here. Actually, I use VI, not Vim, and that's one distinction that Gust1 definitely makes a lot. Okay, these are both 3 elements. It should be okay. So we do n 0 to n minus 1. Should be okay. I see no reason why that would be an issue. Then we divide by n total in the end. Yep. -2 imaginary pi. The factor seems okay. And again, it's weird here that we have most of the values working. So if we run Cooley-Tukey, let me see. Let's say x is going to be equal to, what was I doing before? 0, 1, 2, 3. And we see Cooley-Tukey, misspelled it, of x. Oh, well that one broke. Oh, that's because I forgot to include it. 1 second. Include up here is somewhere up here. I promise. Here it is, include. And now let's run it again. Cooley-Tukey of x. Again, the issue is kind of weird here. VI and Vim are awesome, but if you tried Emacs, I don't even know how to close it. There is a huge debate between Vim and Emacs. Like, the church of Emacs is huge. Yeah, it has to be in the cat command. That has to be how it is. I could try 2 instead of 1, but I don't think that'll do it. Let's go include Cooley-Tukey. Yeah, so all that did was split it up into 2 different sides. The issue is just that first number, the third number is out. And that's the one I can't quite figure out, why the third number is wrong. We could be ignoring it. So let's go here and let me see what happens if we do half plus 1. Well, this should pop up an error. Include Cooley-Tukey. Yeah, so that one pops up an error. We have to do half plus 1. Richard Stallman is not my father. He's nowhere near like high on my ranks of things that, or of people that I actually would care to talk to. I mean he's cool and all. It's just he's not my thing. Okay, -2 pi 1 to 2. Yeah, so this is just going to be basically debugging. But guys, I think I'm going to go ahead and end here. We do have a bit of a bug. That's fine. But I think today was, on the whole, a success. So we got through a lot more than I typically would have. We are almost done with this. It's just a small bug that I can't seem to figure out. And again, guys, I'm going to try next week streaming just Monday, Wednesday, and Friday instead of every single day like I normally do. This should allow me to adequately prepare beforehand. Basically, the idea is that I implement all of the hard parts the day before. And then the day of, I actually go through and I just implement everything, so I don't have so much wasted time, you know, kind of like I had today. So we don't have so much wasted time. Try VCAT? Yeah, we can try VCAT. But I think, let me see, include Cooley-Tukey. No, see, it's still a positive 2. It should be a negative 2. Yeah, that's fair enough. Okay, so that's the idea. From now on, guys, I'm going to try, or at least for this upcoming week, I'm going to try to adequately prepare before every single one of my streams. Because honestly, the first hour or so of today's stream was actually great. Remove the 1. Let's go to include. Cooley-Tukey. Yeah, I think we're just missing an element. I think we're totally just missing an element. And I'm not sure why. Even, odd. Let me just go up here real quick. Let me just print line length of x odd. 1 second. Of length of x odd. They should obviously be both of 2 in length. Include. Cooley-Tukey. Yeah, they're both of 2 in length, so that's fine. Yeah. I feel the opposite. Maybe that will help, won't it? I think James' best streamer really explains well and helps because the troubleshooting is more helpful for me to watch. Maybe. So here's the thing. I do a lot of troubleshooting on this stream. It always ends up being that I know where I'm going and then I always end up screwing it up at the end. And I just don't want to do that anymore. So I'm just going to cut down on stream time. We'll see how it happens. If it happens that that the streams are of no real better quality and you guys prefer the old way of doing it, I can see about going back to streaming every day. I just want to try it as an experiment for this upcoming week. Outside of that, guys, I realize this is still kind of sort of not quite there, but that's okay. We will continue working on it I will continue working on it, and then I'll kind of put it up on GitHub when it's done, and we'll probably discuss it on the next episode. Speaking of the next episode, it will happen Monday night my time, which is Sunday night your time. I will see you guys then for the next episode, which I haven't quite decided what we want to do. It could be applications of FFT, or it could be some sort of machine learning thing. I haven't quite decided. There's a whole bunch of things that we could do. Run reference of FFT implementation, simple and efficient. Sounds good to me. So we'll take a look at that in a bit. Okay, so with that, guys, I'd like to thank you so much for watching. Have a great day, night, afternoon, morning, evening, and I will see you guys next time for the next episode of Simuleos, where we continue working on well, maybe not continue working on, but we work on something new. Again, the idea is that I want to kind of finish something in 2 hours from now on, instead of kind of leaving it at cliffhangers, kind of like unfortunately today was. That just means more preparation time on my part, which is why, again, I want to lower the stream frequencies. Anyway, thanks so much for watching. See you next time. Bye, guys.